Now we're going to listen to Hristo about diversity preserving clustering method.
Thank you very much, Jean-Michel. Okay, like this. So indeed, I'm going to talk about diversity preserving clustering, and this is joint work with Tassio and Jean-Michel. I was having the honor to be the last one. I'll keep it light and...
No,
okay.
Me imagino que no estás viendo nada, ¿no?
No.
No.
Tenemos que compartir la pantalla. Disculpa. No lo he hecho, disculpa. Lo puedes hacer. Así compartir pantalla. Aquí. Aquí. Pam. Compartir. Y me imagino que ahora sí funciona.
Ahora sí, sí, gracias.
Perfecto, disculpa.
Well, again, this is a joint work with Tassio and Jean-Michel. And I want to start with a small outline of the talk. So I'll begin with a little historical justification about the need of fairness in machine learning. So Paula and the previous speakers have covered a lot of it, but I try to make it interesting. And then I'll talk a little bit about a different problem, not pair supervised learning, but pair unsupervised learning. So we don't have any ground truth. And then I'll talk about how we try to approximate the problem with some methods that we call attraction-repulsion clustering. So from the previous talks, slight look around yourselves, and of course your own experience, you wouldn't blame me if I tell you that technology is absolutely everywhere. So it is omnipresent, and of course its effects are more crucial in our daily life by each single day. However, this hasn't been the case always, okay? So this has been the result of decades of decisions and of hard work. And how did we get here? Well, first we had crazy improvements in hardware and in infrastructure. That is, we went from the mainframe, which was room size, to the smartwatch, which of course you can wear in your wrist. But also the amount of information we can share went from the kilobytes per second to the gigabytes per second, which is an amazing improvement. So we are more and better connected than any single point in human history. Not only we improved our hardware, but also our machines became smarter. How that came to be? Well, we showed them how to learn patterns from pre-existing data. Okay, and with that came the boom of machine learning. And well, the problem is, a tiny problem is that we don't know how we learn. Okay, so we don't know that, but we were able to show to the machine how to learn. Okay, and how did that happen? Well, we used, of course, approximations or shortcuts. And which kind of shortcuts? Well, instead of looking for causality, we settled down for correlations in huge data sets. Okay, since finding data, well, doing your own data is quite expensive and hard. Well, we settled down for finding the data in the wild. The data that was already there was the one that was used. And of course, instead of carefully annotating the data, even the wild data, we didn't do that. We used proxies and implicit feedback. So this means that instead of asking a user why he clicks on something, we just assume that he was interested because he clicked. Okay, so those are the proxies. Of course, we've seen huge improvements in technology, and this has been widely successful. But of course, as any revolution, after some time passed, we started to realize that it had some drawbacks, okay? We started to experience the negative consequences. And some of these negative consequences are listed here. Some advanced consequences of our learning, our technological revolution, were that we were constantly surveilled by IT companies. It doesn't matter if we give our consent or not, we are constantly being monitored. Of course, as Paula and the other speakers have said before, data in the wild faithfully reflects our biases, okay? So that's how Twitter bot becomes racist, misogynistic, and so on, because it basically represents what people fed him, okay? Of course, we have huge imbalances in information, because companies and developers have know a lot about essential points in the algorithms that take fundamental decisions about our life. Okay, so there's a clear lack of transparency. The same imbalance in information leads us to be easily manipulated, as, for example, experiments by Facebook show. And of course, we have the clouds and all the gadgets we use, which are extremely energy demanding. Okay, so of course there is an effect on pollution. So these are all the externalities that when we developed algorithms, we didn't care too much, but now we're starting to care about. Okay, so I'm going to talk especially about the part that is concerned with bias, or on the opposite, with fairness, of course. And I'm going to talk a little bit about the fairness in machine learning, starting by the essential. What is fairness? Okay, so it's an impartial and just treatment or behavior without favoritism or discrimination. Or nice definition. However, of course, fairness is not a clear-cut concept. Okay, it's not like we know exactly what is fair in a situation, because it doesn't happen like that. No, it's circumstances are important. And the context is important, okay? So the same decision may be fair in some context and maybe unfair in other contexts. So you have to ask what are fair data and so on. So it has to do with how we interpret some parts. Even more, fair learning, fairness in machine learning has to be implemented in the whole workflow of the machine learning procedure. That is, we need to check for bias in data. We need to make sure algorithms. So we need to make sure that we are not putting biases, for example, from the developers into the algorithms. But of course, we have to check also the results and feedback. Why? Because the results of the machine learning that we do now is the data that we train future algorithms. So we need to check also that part. And of course, what does happen if I've been mistreated, I've been unfairly treated, who I complain to by some organization? Okay, so we need a proper legal system to be able to address these fairness concerns. Okay, so this has been the historical introduction, and now we go to closer to the main points. We are going to talk about algorithmic fairness, because of course, because solving all this, it's not the purpose of mathematicians. Okay, it has to be multidisciplinary. Different people have to work together to solve this problem, because it's not a point. It's not a question of just doing fair algorithms, because there are many other problems to address. However, well, I'm a mathematician, so I try to address algorithmic fairness. And the data, as Paolo said before, there are some attributes that are unprotected, which usually are the ones we want to use for the algorithm, and there are some protected ones, or sensitive, which are the ones that may suffer some bias, basically sex, age, race, and so on. And then, with mathematical fairness procedures usually do, they take a mathematical definition of a proxy used for fairness, okay? So it's not like we know what fairness is and then we do mathematics with exactly the definition of fairness. No, we do a mathematical proxy, an abstract way of defining some approximation of what we think is fair. Okay, so this is like, it's not just a clear-cut problem and as easy solvable as just doing better mathematics. So we have demographic parity, which imposes in the supervised learning field, it imposes independence between the predictions of the algorithm and the sensitive attributes, equalize out, which imposes independence between the predictions and the sensitive attributes, conditional to the actual outcomes, equal opportunity, which is the weaker of all the ones I've listed, which basically means that the true positive rate has to be equal for every class of the protected attribute. However, there are many more mathematical definitions which sometimes are incompatible between each other, so they cannot be imposed at the same time for the same data. And of course, you should choose wisely what is your criteria for fairness, because this depends on what you want to do. Now, finally, I arrive to what you want to do, which is fair unsupervised learning or fair clustering. And the idea is to group the data into the joint sets in a way that we can impose some fairness requirement. And of course, the first question should be what type of fairness required? What fairness means for you? Well, as Paula said previously, demographic parity is the usual one, a nice one, and it can be, well, nice one, it's the usual one, a common one. So demographic parity can be pretty simply adapted to the clustering set. Well, how do we do that? Well, we ask for cluster to have the same proportion of individuals in any cluster for any protected class, and it should be the same proportion as the one found in the total data set. Okay. And basically, what this means is that clusters should be independent of the proportion of the independent attributes. Okay, that's a way of seeing it. I hope it will be clear in the examples. And now the important point here is that we are just trying to preserve diversity in any single cluster, and that's the proxy you're using for fairness. Okay, here you're saying that if you keep your diversity the same in each cluster, you're being fair. So you should know that that's what you're doing, and that's what you have to ask of your algorithm. Well, another problem, not only fairness is not totally well-defined, but clustering itself is not a well-defined problem. What do I mean by that? Well, the notion of cluster is not clear-cut. There is no like a standard agreement what is cluster. So you can, depending on how you want to use your clustering algorithm, you may just want to group the data into different groups. Okay? So if grouping your data into different groups is the point, you can use fairness fairly easily. And that has been done mainly in the literature, okay? However, if you have some existing structure in the data, that is, you have some natural groups, then adopting fairness, it's not as easy. That is something similar to the supervised learning when you have the ground truth. Here, having structures, some kind of ground truth, so things get more complicated. So let's settle everything down with some examples. I hope you can see that this is black and this is red, yes? Okay. So, what is this? This is a data set when the x-axis and the y-axis are the unprotected attributes, okay? Circles and squares are the protected attribute, which is just the shape of the point. Well, then we have done a standard k-means looking for two clusters, and what we obtain are the red cluster and the black one. Right? Is this fair or is this not fair? If diversity is what we want to impose. I have to tell you before that in the total population there are 50% of circles and 50% of squares. So is it fair or is it not fair? Well, okay, I'll say it's pretty fair. Why? Because we are preserving diversity. Our definition is that here 50% of square, 50% of circles, 50% of square, 50% of circles. So this is fair. But also the k-means is capturing the structure of the data. Here, clear clearly two separated groups of data, okay? So you're capturing that. But now I go to this different set, same situation as before. Okay, proportions are the same, everything is the same. But there's no structure, apparent structure, okay? So let's not get too crazy on that. There's no apparent structure. What happens now? K-means work perfectly. It is absolutely fair. But I split here, it's absolutely fair. I split here, it's absolutely fair. Basically, anything is absolutely fair, okay? So now, here, the task is not to find structure, it's to group the data, okay? So I hope now you understand the difference of what you want to do. For example, many fair clustering procedures are just applied to the adult data, okay? But the adult data doesn't have any structure, doesn't have any cluster, okay? So measuring a fairness in a data set which has no clusters is like, well, you'll perform well because there's no structure. Now comes the problems coming. So what happens here? Same situation, but now we have here circles are overrepresented and here circles are underrepresented. So this is unfair by demographic parity. Okay, but the k-means, again, standard k-means, is capturing the structure perfectly. Now we have a problem. Is this fair? Is this unfair? It depends what you want to use it for. Okay, that's the whole point. That's the whole point. Okay, so you have to be careful what you wish now when you want to impose fairness. And then the extreme case. This is again the same situation, but now we have completely homogeneous clusters. And now there's no way of preserving the structure and imposing fairness. Okay, there's no way. You want to do the last extent by a center to impose independence, conditional independence. It goes here. All distributions are the same. They are completely mixed. No way of preserving the structure which is there. So this data is biased or not? Well, it depends. It depends. Again, it depends. Structure and diversity may be concepts that are antagonistic. Now, the idea is that we should make some trade-off between structure and fairness. Okay, and we want to do that by transforming the distance structure of the data. Okay, by preprocessing the data. So the trick, it's a simple trick, and the idea is just to change the distance between the unprotected attributes using the protected ones in a way that favors diversity. Okay, so we won't try to reach perfect diversity in the data. We want just to favor it, but trying to respect the structure of the data. So how do we do that? Well, we introduced perturbation of the standard Euclidean distance between the data points using an additive perturbation and then a multiplicative one, where we have some free parameters to govern the intensity of the perturbation. Okay, so our idea is just let's change the distances using the protected attributes, and this is kind of inspired by physics. When we try, and you'll see why when I use the examples. So to settle down what our diversity, our attraction-repulsion dissimilarities do, the protected attributes are in -1 and 1, and for our additive perturbation, we just fix a positive constant. Okay, and then the distance is the same when the protected attributes are different. Okay, but we have an additive increment when they are different. Okay, so it's kind of a repulsion. So you have the same class, you're further away suddenly. And you can do the same trick, but in a multiplicative fashion with our second dissimilarity, and we introduce a couple more dissimilarities. Those are classes of dissimilarities, and you can do more if you wish. Okay, so and that captures the same concept. Well, we can do this using the kernel trick. We can do this when the cluster structure is not as simple as usually, and basically more complex cluster structure. Fine. And how do we do our procedure? Well, it's very simple. We just calculate the dissimilarity matrix, choosing appropriate dissimilarity. and we're choosing appropriate parameters, and then, if necessary, we do an embedding into non-Euclidean space using multidimensional scaling. So we basically try to embed this dissimilarity structure to a distance structure, and then we can do any standard clustering procedure. Okay, this is an advantage of our method. It can use any standard software for clustering. Okay, so this is nice. Again, now I want to give an example, and again, it's a philosophical example. So we have here the Ricci dataset. I hope you can see the colors. This maybe it's black, green, red, blue. So the axis, the x and y axis, are the scores on an oral and written exam of firefighters, and these results were crucial for promotion. Okay, for internal promotion. And again, the race of the participants is codified by the shape of the points. So square are white, and points and circles, sorry, are Hispanic and black. Now, if we wanted to group the data into 4 clusters, we can use standard k-means. Okay, here we have it. Then we can use our procedures with appropriate parameters, and again with k-means, and then we can use a completely fair with respect to demographic parity. A procedure completely fair with respect to demographic parity. What do you see? Well, our procedure is kind of in between of the two partitions. That means that we preserve some kind of compacity. Clusters are compact, the variance is lower than the whole data, and we improve some. We get some improvement in diversity. Okay, it's not, the numbers are not here, but this improves considerably the diversity with respect to the k-means. And however, we see that, for example, the completely diverse case groups are very, very mixed. Some of them have almost the same variance as the total data. Okay, so they are not looking for compact structure. So so again, which one is the best? Well, it depends. It depends on what you want to do with it. So you have to be very careful when choosing your objective, when doing fair clustering. And the last example is a real data set again. When you have the locations of all the schools in New Jersey, well, they're entry level, middle level, and high schools in New Jersey. And we want to group them by location, but also by racial composition. Okay, so we have the racial composition of the school, which have 6 types of races, and we can use this information. And we see that we obtain very different partitions for different level of intensity in our perturbation. We see that standard k-means just looks for locality, so clusters are very consistent with the spatial distribution of the schools. And then if we impose some slight improvements in diversity, we want slightly more diverse groups, we get locally consistent groups. They are compact and the variance is low, but they are not much more fair. And if we want more fairness, we have to destroy a little bit the structure of the data. So our procedure is able to go in the spectrum of all these cases. So it has some. It gets a trade-off between fairness and structure. Well, this is the bibliography, where the introduction was based on Christina's work, machines we trust, and the rest of the talk was based on our work. And I thank you for the attention at these late hours. Thank you very much.
Any questions, any comments?
I have a question. So, is it possible, let's say I have my data and I want to create 3 clusters. Is it possible that having 3 clusters and respecting the fairness definition are incompatible?
Yes, that's exactly, yes, as we showed before, and the ones it can be replicated in with any number of groups, any number of protected variables. It's just that the structure is maybe compatible. Basically, if you want to think of it, all the bias is the thing that gives structure. So if your bias defines your structure, if you eliminate the bias, you eliminate the structure. So that's the heavy way of thinking about it, but it can happen.
Okay, okay, thank you.
Thank you very much for this lecture.